Okay, we're live. We're live from New York. I wish we were live from New York. We're not. We're live from Odessa, Texas. It's hard to get in there. Okay, we've discussed all of these things, at least this part here. Diffusion, anytime you're doing a diffusion, you're moving something from where you have more of it to where you have less of it. And whatever you're moving it across is not a barrier. Like the cell membrane is not a barrier to oxygen. It's not a barrier to CO2. So, the oxygen can move out, the CO2 can move in. But you're always moving something from where you have more of it, a high concentration, to where you have less of it, a low concentration. And like we said yesterday, that's down the concentration gradient. That's what they call it. So that's what they're telling you here. Down the concentration gradient. So here you have it. Someone put dye in, probably we'll say this is a dialysis membrane, be my guess. And then it's going to move. It would be small enough that it could pass through the pores of the membrane. And it just is a random movement. Actually, it has a name. It's called Brownian movement. All molecules are in motion, believe it or not, even though they may not look like it. The table that you're sitting at is in motion. It doesn't look like it. It doesn't move far, but it is in motion. So things do move. And eventually, those dye molecules will eventually pass through the pores until they do reach a state of equilibrium. So we're going from an area of high concentration to an area of low concentration, and that is a simple diffusion. Now, passive transport, that just tells us we don't spend energy. No ATP. Our energy that we spend to do anything is always ATP. That's what we do. And if you don't need the energy, it's passive transport. So some of what we saw yesterday was actually passive transport. Let's go back to this right here. That's a diffusion. So that's passive transport. I don't need ATP for that. Let's see. Yeah, this right here, the channel protein, where you're moving something from where you have more of it on the outside of the cell to where you have less of it on the inside of the cell. That is a passive transport, but if you need some protein to help you do that, that's called a facilitated transport. We did talk about that. Now, in an active transport, you're moving something from where you don't have much of it, which in this case is this red sphere inside the cell, and we're moving it to where we already have more of it, which is outside the cell. We're going against the gradient. We're going from low concentration to high concentration. And in order to do that, you need a protein to help you do that, and you also need some energy to go from a low concentration to a high concentration. That does require the expenditure of ATP, so that is why they call it active transport. So if it's a diffusion, that's going to be a passive transport. If it's a facilitated diffusion, that is also going to be a passive transport. No energy is required. Now, when we get into osmosis, that is simply a diffusion of water. Water moves from where you have more of it to where you have less of it. That's about as easy as it can get. So things move from a high concentration of water. It specifically deals with just water to where you have a low concentration of water. So where we have less water to where we have more water. It's a diffusion from high to low concentration, but it's not a diffusion of oxygen. It's not a diffusion of carbon dioxide. It is a diffusion of specifically water. That's what we've got. So they specifically call it osmosis. And for some reason, people tend to think that's complicated. I did. When I was, I don't know, in college or at some point, I was like, osmosis. I don't really understand it. What? I look back on it now and I go, what? I didn't understand that? What a goof. I must have been the world's biggest goofus, because I just was like, what? I don't know what he's talking about. Well, you move water from where you have more of it to where you have less of it. Da-da. Hello. Wake up, you stupid ass. I was talking to myself. basically. I'm talking to myself. It's like, wake up. You know, that is not hard. That is not hard. From higher to concentration to lower concentration of water, of just water. You know, and I honestly remember, you know, I don't really understand this osmosis thing. I don't know. It is weird how you know, things become very, very understandable at some point in your life, and you're like, well, why did I have difficulty with that before? Why was that tough? I don't know. But so I definitely understand if you're like, you know, I don't get that whole osmosis thing, you know. If you know, if someone were to come in and say that, it's not like I'm going to judge you or anything. I'm just going to go, yep, been there. Definitely been in that spot. Okay, so what's happening here now? These little purple spheres that they have inside this U-shaped tube, they cannot move through the membrane. They're not going to move. So if you count how many we have on the, let's say for you, that would be the left side of this here, and on each side of this membrane in the center, and how many you have on the right side, that's exactly the same number of purple spheres you have on the left side and on the right side, or at least it should be. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. So you have exactly the same number. So whatever this purple sphere is not going to be able to move. It's too big. It can't pass through the membrane. Water, however, is very tiny. It's only 3 atoms, so that's incredibly tiny. So water can move. So water's going to move from where you have more water to where you have less water. So on this side, let's see, you can see you've got more water. So over here, you've got how many? 2, 4, 6 of these purple spheres. So we don't have a whole lot of water here. I mean, we have a whole lot more water here than we do on the right-hand side of this. You really don't have as much water. And so that really deals with concentration. So if this is my solute, let's say those purple spheres, if that solute concentration, let's say it's, I don't know, we've got 2, 4, 6. So let's say it's a 6% solute. That would give me a 94% water on that side. Let's look at the other side of it. I've got 2, 4, 6, 8, 10, 12, 13% solute. And then that would leave me with a 87% water. Okay, so when we're talking about if the solute cannot move, then the only thing that can move is the water. Water's going to go from where you have more of it, in this case is 94, to where you have less of it, in this case is 87. So water's going to move through, and in doing that, you can see that one side is going to actually elevate, the water level goes up. And that's to try to create an equilibrium with the water, so you have the same amount of water on both sides of that membrane. So the water does pass through. This level will go up, and you try to reach an equilibrium with that. So that's just a diffusion, again, of water. It's just an osmosis. But keep in mind that you have to, in that case, you have to consider that the solute is not capable of moving across the membrane. Because if it were, you really have movements both directions. You have the solute able to move, plus you have the water able to move, so, you know, eventually it would all level out completely. The solutes would be the same number on each side, and the water would be the same amount on each side. But in this example, they're saying that solute cannot move. So we have to try to equalize the water concentration, so more water moves from high concentration, 94%, to the 87%, and it moves to equalize that. So, and you could do this in a lab. It's pretty easy to do. It's not hard to set that thing up. Of course, we didn't have time to do it, but that is not anything new for this semester. This term right here means the concentration of the solute, not the water, tonicity. equals concentration of whatever is dissolved in the water. So equals concentration of solute. Now we've already discussed this in lab, so hopefully this won't be too incredibly complicated. If we say isotonic, iso means the same, so same. So this is same concentration of solute, whatever's dissolved in the water. Same concentration. So if I have a cell, and most cells are about a 1% solute, that gives them a 99% water. To have isotonic, then the solute has to be exactly the same concentration outside the cell. That's a 1%. Obviously, that gives me a 99% water concentration. The problem is, most water that an organism would live in, now we don't live in water, so it's really not a huge deal for us, although we do have to have water regulation. If you lose too much water, you're sweating, you have to drink water, but so far we can get it, right out of our refrigerators, nice and cold, very tasty, purified water. That's what it says, purified, so they took the bugs out. No bugs in there, supposedly. So most organisms, if they're aquatic, they're not living in a 1% solute concentration like fish. They're living in a 3% solute. Ocean is about a 3% salt, approximately. So the concentrations are different. So they're having to regulate their water concentration because what they have to swim in is a 3% solute. They only are swimming in a 97% water. So let's look at that. In that case, the water has more solute than the fish does. And that's what you call a hypertonic solution. And hyper, of course, means more, greater than. Have a hyperactive child. That's one that's kind of bouncing off the walls. I'm pretty hyperactive most of the time. So that is a greater than, more than concentration of solute. Things dissolve. So let's look at that. So we have a fish, let's say, for example. This fish is a 1% solute. That means it's a 99% water. Now these are bony fish as opposed to something like a shark, stingray, manta ray, a whole bunch of rays out there, electric rays. We can go on with that. All the invertebrates, your jellyfish and animals without backbones, they're typically about a 3% solute. Well, the ocean is a 3% solute, approximately, depending on where you're located. But on average, it's about a 3% solute. That's a 97% water. Okay, so this fish is swimming in a 97% water. So the water concentration of the fish is greater than the water concentration that it's swimming in. So osmosis tells us water is always going to move from where you have more water to where you have less water. So water is going to come out of this fish and go out into the ocean. It will dehydrate the fish. If the fish didn't have a mechanism in order to retain water and to pull in more water and retain that water, and it's constantly battling this, it constantly has this water moving completely out of its body, and it has no control over that. That water's going to always be moving out of his body because his cells are 99% water. The ocean is 97% water. So water's moving out, always. So they have to have mechanisms to ensure that they can, and the way that they really do that is they're also taking in a 3% salt, which is the ocean salt. So they're consuming that, and so they try to eliminate that salt. And if they can eliminate that salt, the 2% out of the 3%, then they only have the 1%, which brings their water concentration to a 99% water. So, we're not just talking about isotonic and hypertonic and these kinds of things because we don't have anything else to talk about. This relates to real world. Most of the fish that are swimming in the ocean are 1% solute. The ocean is a 3%. They all have problems. They better develop some way to deal with that situation, or they will lose their water, dehydrate, and they would all die. Not good. I don't want all the fish in the ocean to die, come washing up on shore, and then I wouldn't be able to get my mahi-mahi at a restaurant. I don't know. There are worse things. Not being able to get mahi-mahi, I suppose, but, lots of fishermen out there survive on being able to catch fish. So, very important mechanisms. So, and we're not at a point where we talk about those mechanisms just yet. We've got one more type of tonicity to deal with, and that is hypotonic. Hypotonic. Hypo means less, so less concentration of solute. Reads like a sentence. Less concentration of solute. If you know what tonicity is, you know that's concentration of solute. You know what hypo is, and I think most people do. Hypo, less than, so less solute. So if I have most cells, let's try this one. Let's put a shark. All right, I love this one. Okay, so let's do this deal. We'll try something else. So I'm going to try to draw a shark. You'll have to bear with me. I'm not a good shark drawer. Not bad. All right, he's got to look mean. Okay, that's not just your regular old fish. That's a shark. Run! All right, shark is a 3% solute. All right, do y'all not have panic going into the ocean? I do. It's like, really, I can wade along the edge of it up to my knees, but when it starts to a point where I can't really see, I don't feel so comfortable. I will do that. I will swim way out there, to the point where the lifeguards on Malibu Beach are going, brother, you are out here with the surfers, dude. You need to come in. You don't have a surfboard. You'll get hit in the head with a surfboard. You'll die. You have got to come in, So I do get out there. So I guess I'm not that afraid of sharks. but anyway, I do think about it a little. But you're more likely to get run over in Odessa, Texas, by an 18-wheeler than you are get bitten by a shark, right? I mean, seriously, we all live here. We understand. Okay, so this is a shark, and if he's in the ocean, he's in a 3% salt, 97% water. But let's take the shark out of the ocean and let's throw him in our swimming pool. Ta-da! There you go. We want to keep our own little shark, right? That swimming pool isn't anywhere close to 3% salt. You may put some chlorine salt in there, but unless it's horribly, horribly, horribly salty, it's not going to be a 3%. Okay, so let's say the water in a pool is, let's say, a 2% solute, some sort of salt. Some people use bromine, some people use chlorine, some people use saltwater pools. That's kind of a newer way to treat it. But the salt concentration isn't nearly like what you would get in an ocean. It's probably about a 1% salt, if it's even that. Pretty low concentration. So saltwater pools, I think, are pretty cool myself. I like them. Pardon? It has a whole lot to do with the runoff into the ocean. The salt that's being carried from the land going in there, and then you get a lot of evaporation, and it's becoming more and more and more salty. It's also becoming more and more acidic, which is why they're beginning to have all kinds of problems with the coral reefs. You need a what? You did? Well, come here, bend over. Come on. Let's get this over with. Right. That isn't going to work. That just, we get rid of that into a vessel, but that doesn't go down the sink. Into a brown bottle, and with a top on it, and just put waste. Well, don't don't let's not damage the what you're carrying in your uterus there. You nasty girl. Anyway, okay, so that's a 98% water. All right. So even if it's in a swimming pool that's that much salt or chlorine or bromine, whatever it is, you're going from a 98% outside to a 97% inside. Water is automatically going to go into this shark. It's going to blow up like a balloon and just die. These cells are going to fill up with water and fill up with water and fill up with water until it's just dead. It can't possibly survive. You can't take sharks out of oceans and put them in swimming pools. Doesn't work. People are like, oh yeah, somebody took you'll be on vacation somewhere and you'll hear at the breakfast, place, oh yeah, somebody took a shark and they put it in the swimming pool last night. Yeah, it was crazy. You should have been in there. They were all drunk and high and da-da-da, And I'm like, yeah, right. Yeah, cool dude. Yeah, right. Whatever. Yeah, tell me another one. Why don't you? What? Who? The Dead Seas? Yeah, something like that. That's kind of like the Dead Sea is sort of like has such a humongous concentration of salt that very little, if anything, will live in it. Yeah, very little. In something like the Great Lakes are like a 15% salt concentration. That's an 85% water concentration. Those fish have so much difficulty surviving in that water, but they do. They do survive. And I've swam in the Great Lakes before, just as a kid. You're just going, oh, look, it's a big old ocean. You can't see the other end of it. It's not like a lake in West Texas, It's just like huge. The earth turns before you get to the other end of the lake. So you're like, oh, great, it's the ocean, and you dive in, and you're used to opening your eyes in the ocean because you can. You open your eye, and it's like 15% salt just goes, keen. Like somebody takes a salt shaker and just goes right into your eyeball. It is not cool at all. Anyway, this shark isn't going to make it. He's just going to fill up with water and die. But he has ways because, he wouldn't be able to function with this. But normally, like I said, if he's in a normal ocean, 3% salt, 97% water, he's isotonic. He doesn't have any trouble. But you throw him in a swimming pool, this guy's in trouble for sure. Okay, so that's a little bit about hypo, that kind of deal. And I know we did that in lab. This is just hopefully a review at this point. So there are those terms. Osmoregulation, that's what we were talking about. Being able to regulate your fluid, your water concentration within the organism. And not all creatures on the planets are human. I know we think we rule. But you have lots of creatures out there, and ocean occupies certainly a heck of a lot more mass than does the land, so there are many, many ocean creatures than there are land-dwelling creatures. So, and they all have their own little dilemma. They have a dilemma, depending on where they live. Like I said, you do have fish that live in a 15% in the Great Lakes. Salt Lake City, the lake at Salt Lake City, Utah. That's about a 15%. Huge salt concentration. The fish that are in there, they're like any other fish. They're 1% solute, and they're swimming in the 15%, which is only 85% water, and their bodies are 99% water. You talk about hard to difficult and very difficult to regulate your water concentration. That would just be tremendously difficult. So yeah, creatures have to be able to deal with these situations, and it becomes very, very, very difficult. And obviously there are those that have managed through evolution over millions and millions of years to be able to do it. And, my hat's off to them. They survived. But you're not going to get a shark to evolve in a period of one night and going from the ocean to a swimming pool. It won't evolve that fast. He'll be dead. Facilitated diffusion, we did do this already, facilitated diffusion, and I showed it to you. Let me see if I can get to a point where we had it. Let's see, is that it? No, that's not it. Yeah, this right here is a facilitated diffusion because you are moving something from where you have more of it. In this case, we got 1, 2, 4, 6, whatever those things are, outside to where we have less of it inside. But you need some help to be able to do it. So we have a protein, and in this case, it's a carrier protein or a channel protein because it's got a hole through it, and then those can move through. But so you're going from high to low concentration, from where you have more to where you have less, but you need a protein to help you do that. That's called facilitated. It helps to take care of that process. So that was a facilitated transport, and I know we talked about that. But well, isn't that cute? It won't erase. All it does is just. There we go. Thank you. Yeah, I knew it'd cooperate. Scream at it long enough. I have a friend that lives there, actually, and I've gone on a cruise out of Galveston and coming back in, which is absolutely horribly disgusting because on the cruise out, we left it at when was it? During the daytime, and I guess I was too busy looking over the ship and see, where the pool was and where the pool was and where you get pizza and where you get pizza and where the pool was and where you get pizza. Those are the only two things I needed, or besides the bars, and those found out where all of those are located. The bars, the pool, the pizza, that's really my triangle on a cruise ship. Well, what really disturbed me was that on the way back in, we came in real early in the morning. It was still dark, and all these oil rigs were out there, and you could see them. They were all just brightly lit up, and they were just everywhere out in the Gulf, just all over. They were just, you could see them for miles and miles and miles and miles. Offshore drilling just made me want to puke. Pardon? Yeah, it's awful. It's awful. What we're doing to the oceans, I don't even want to get into it. I don't want to break down and cry in front of all y'all. I'm supposed to be an adult. Like, oh man, let's not do that to the world. Can we? Can we just not? Anyway, so here again you've got facilitated diffusion. You're moving something from where you have more of it to where you have less of it, and it requires some sort of a protein in order to take that from a high concentration to a low concentration, and that is once again a carrier protein. A transport protein. Okay, and if we're moving water, it does move through a protein channel. So if it's doing this, but these things are not solutes, these are water molecules. Water has these proteins which are channel proteins that just specifically allow water to go through, and they're called aquaporins. And, you know, that was something that didn't come out until like the last 5 years, maybe 10. I don't know. It's been relatively recent that that information was even discovered, that you had proteins that had holes for water to move in and out of the cell. So that was very cool for someone to locate that and be able to put that in a book. I mean, wouldn't you have loved to discover aquaporins? I would. You know, and that was just, you know, during your lifetime. Someone came up with that. There's so much left out there that needs to be discovered. And we tend to think that, oh, everybody knows everything at this point. No. The knowledge base continues to expand, but you know, what we know is just minute compared to what needs to be known for sure. And I don't see that changing anytime soon. Okay. So active transport, we did talk about that. Active transport, you need these things. For one, you're moving something from where you have a low concentration of it, from a low concentration, whatever this substance is, and to where you have a high concentration, to where you already have more of it. I give an example of calcium. Moving calcium from the blood into the bone. Your calcium concentration in bone is tremendous. So yeah, you're having to go uphill battle from low to high concentrations. You already have a whole bunch of it there. So not only do you need a protein, so you got to have a protein to make that work, but it also requires energy in the form of ATP. So you got to go from low concentration to high concentration. You need a protein, plus you need energy, because really you're trying to push it uphill. You're trying to get it into an area where you have an abundance of that. And that's not the only example we could give you, but that's probably one that most people could easily identify with and go, okay, I get that. I get that. Yeah, that's something I get it. I can see how that would require energy to do that. And some sort of protein to make sure it could get into the bone. So, yeah, that's not bad there. Okay, now, this is this isn't as complicated as it looks. Most of these things, that when they pop up, you're like, oh my goodness, I've just stepped into a pile of my cat's poo. You know, I got a new cat, and that cat makes the worst smelling poo you have ever smelled in your life. Oh my God. You know, he'll come out of he comes out of the laundry room, which is where the cat box is, and this space that I live in is fairly large here in Odessa, and within 10 minutes, it has permeated the entire space. Doesn't matter what room you walk into, it is everywhere. It's like poo all over the place. So, you know, anytime he goes in there to poo, I'm just right in there following him, like, you know, like with something to get that out, because I don't want to smell that. Nasty poo, nasty poo. And he's got gas, too, I'm telling you. He has got gas. And he's been to see the vet. I've already tried to fix this problem. We're working on it. We're working on it. He's costing me money, but I am not going to smell that gas or that poo. This has got to end. This has got to stop. Oh, you know, you could just rinse it with petroleum ether and put it in the same jar. Yeah, that'll get it. Yeah, that'll work. Yeah, you feeling better? Okay. All right. Remember, she finds out today whether it's a boy or a girl today. Today at 3 o'clock, so I'm going to know by 3:05. and we still won't know who the daddy is. I'm just kidding. and 1. I don't know if I wrote that. If I did, I was not in my right mind. It's been 9 and 1 forever. Oh, yeah, that's not right. 9 and 1. Yeah, I'm glad you asked. Okay, so here's an active transport. Notice we've got some sort of a transport protein, and we're trying to take the little green squares to the opposite side, transport those out of the cell. So notice the transport protein actually does change shapes, and that's one way that they can function. So the green square, which is the solute, goes in, and then it changes shape so that then it can be released to the exterior of the cell. But it also, you are going from where you have less of it, less green squares, to where you have more green squares. So you're going from a low concentration to a high concentration. You do need a transport protein of some sort, whether it's a channel protein or whatever, but you got to have that. But you also have to have ATP. So those are just necessary components in order to make that work. Okay, now, if we want to have what they call bulk transport, meaning we're taking in large amounts of something, instead of just transporting a few solutes in, transporting a few solutes out, transporting a little water in, a little water out, instead of that, then what we need to do is what they call a bulk transport, means transporting large chunks of things. So, for an example, this happens when a white blood cell, so let's say this is a white blood cell, WBC, and your white blood cells are, of course, some of them designed to destroy, eliminate, get rid of things that you shouldn't have in your body. Well, let's say it's a bacterium, so here's a little low bacterium. So what it will do, it will take its membrane and it pulls it to the interior and creates this invagination. So, and really that works because you have microtubules that attach to it and also to the other membrane just to pull it in, and they actually begin to shorten in order to pull that membrane to the interior. So then that bacterium, which I'll do in a different color because it should have been, that bacterium gets engulfed into there, and then what you end up then having is a white blood cell that has a vesicle, again, it's what I call a membranous bag with a bacterium in it. Well, keep in mind we do have the Golgi apparatus that will produce lysosomes, and the lysosomes are digestive. So here's the Golgi, and here's a lysosome, which has digestive enzymes in it. And that will fuse with this and then digest the bacterium, or digest the spore, or digest the pollen grain, or digest the virus. You're just digesting whatever you brought in. So this is a bulk transport. We're not just moving something back and forth across the membrane. We're pulling in large amounts of solid material, and this is an endocytosis to bring to the interior. We can do the same thing if we want to export something. For example, if you wanted to produce, say, a protein, and let's say that we've got endoplasmic reticulum in here, and let's say it's transporting protein, so we have ribosomes attached to it. This is the ER. And we create a bud like that, and this has a protein inside of it. Okay, and that's released, and eventually it will fuse with the plasma membrane, and that will be exported, whatever that protein is. So that continues to move this direction, and then my protein, which is the X thing, is going to be released. So let's So I have the membrane, which is this thing right here, that membrane fused with the membrane of the cell, and therefore whatever was in it, which in this case was some protein X, we'll say X, and then that is exported out of that cell, we get rid of it. So there are times when we need to, of course, export things. Like a salivary gland, you need to export amylase into the oral cavity to digest starch. That's its function, to digest starch. So we have salivary glands that make this stuff and then export it. It's called an exocytosis, to exit. But you're not just exporting something really tiny and it's not just moving across the membrane. You're just like pushing lots of this material out at a single time. And so we have to make a whole bunch of that. We constantly push it out of cells, and we make more. It gets pushed out of cells. We make more, put it in vesicles. They fuse with the membrane, and then, of course, are released outside that cell. Now, that's just an ongoing process. Some things just occur on a continual basis. And we make saliva, we swallow it, we make it, we swallow it, we make it. It never stops. You know, it's a wonder we don't all just drool like crazy at night. You know, it means then that evidently we have to be swallowing because you're still making saliva. So it forms in your mouth, and you get a mouthful of saliva and you're asleep. You know, we must have some built-in mechanism to make us go and swallow that, even though we're asleep. You know, because if we didn't, it'd just be like all on the pillow. The next morning, you'd be like, what in the world? That was nasty. You know, you'd have to buy plastic pillows. Plastic bed sheets. No more of that 600, 800 thread count, you know. Hey, you know, give up on that. Like, what? I can't lose that. Are you kidding me? Not happening. Anyway, you know, I can give up a lot of stuff, but an 800 thread count, you know, bed sheet, forget it. I'm not losing that. You know, I'll just walk to school. Sell the car. Yeah, walk to school. Some things are important. All right, I know that's probably silly, but people have things they enjoy, and that happens to be one thing I enjoy. Nice sheets. Okay, phagocytosis. This means cell eating. Cell eating. So you know, this is an endocytosis. That's exactly what it is. You know, that's what we just did with the white blood cell. It is cell eating, which is a endocytosis. But if we're bringing something in and it happens to be a solid material, so we're bringing something solid, cell-eating solid. Could be a bacterium, a virus, a pollen, spore. Solid. It is an endocytosis, but if it is a solid, we'll call it a phagocytosis. Sometimes we do this very specifically in order to get things that cells need, so they call it receptor-mediated. So you have to have a receptor so that specifically if this thing happens to move past the cell and that cell's like got a receptor for that specific thing, then it will attach to the receptor and be brought into the cell. Some things cells need very specifically, and some things don't. Depends on the cell. Different cells have different needs. You'd think, oh, well, they all pretty much need the same stuff. Well, some things, yeah. But some things they need very specifically depending on if it's a pancreas cell or a liver cell or, you know, depending on where it is, you know, what it's going to produce. They have to get very specific things. So they get receptors to make sure they can pull those things in. So they did give us one here. Cholesterol, take in cholesterol. Cholesterol, you would say, you know, that's something that's bad. It's not. Not until your levels start to go up too high. And at your age, you don't worry about it. You don't need to worry about it. Once you reach 40, then you have to get your cholesterol, triglyceride levels checked. But for some people, it is genetic that your mechanisms for absorbing these receptor-mediated being able to pick up cholesterol and pull it into a cell, because you have to have it in a cell in order to make things. For example, you take cholesterol in order to make a neurotransmitter, acetylcholine, for example. It's an excitatory neurotransmitter, so it makes neurons fire, which is what you may want them to do. Because if they didn't fire, you'd just be like laid out on the floor. Nothing would be working. So cholesterol is used in the manufacture of other things. So we have to be able to make it. We have to be able to take it into cells. And so it's very important that we have receptor-mediated cholesterol absorption. That's absolutely necessary. Pretty much for all cells to be able to do that. They need it. In fact, cholesterol is a part of all plasma membranes. There's a piece of a plasma membrane. There's quite a bit of it, actually. Although it's not. We said a plasma membrane was 45% phospholipid and 55% protein. It's not that high, but cholesterol kind of acts like a wax. It is a wax. That's really what it is. It's a wax, and it binds cell membrane together. It holds it as a unit. Very important for cell membrane function. Okay, we'll at least start energy. Energy is usually called the ability to do work, capacity to change or to do work. Two basic forms of energy, because we're going to get into the next chapter which deals with energy. In fact, on chapter 6, I will not even be using a PowerPoint. I will just be lecturing, because I think the easiest way to get through chapter 6 is for me to just stand up here and go through what I think is most important about chapter 6, because you can spend weeks and weeks and weeks on chapter 6, and we obviously don't have those weeks.